everyone, it's your SI leader Noora here to do a quick problem that has multiple double bonds. So we're given a molecule and we're told that this is the product when this molecule reacts with one equivalent of your hydrohalogen, your hydrobromide. And let's go through why this would be your actual product. So I've written out this molecule 4 times, and I'm going to produce 4 different cation species for 4 different additions of the hydrogen across the different double bonds. And we'll find out why this is the actual product that is produced. So firstly, let's pretend that this double bond here has picked up this hydrogen. Again, same thing, versus if this double bond reacts with our hydrohalogen, which I shall replicate by doing this. So there are 4 different possibilities here for this reaction, this addition of your hydrohalogen across your double bond. Now, your first option is an addition of your hydrogen here, giving you a cation species like that. Your second reaction is, again, addition on that same double bond, but instead of adding our hydrogen there, we're going to add it over here and put our positive charge right there. And then for these 2 carbocation options, we've reacted this double bond with our hydrobromide. And the first option is to put your hydrogen here. And the second option would be to put your hydrogen here. So now that I've gotten all those written out for you, let's look at the varying carbocations, intermediates that we've produced, and try to parse out which one is the most stable. So starting over here with this carbocation, we have a carbon attached to 2 other carbons, so we know that this is secondary. This one is a carbon attached to only 1 other carbon, so this is primary. This one is a carbon attached to 3 other carbons, so it's a tertiary carbocation, versus this one over here, which again is secondary, simply because of the fact that it is attached to 2 other carbon atoms. So Markovnikov regioselectivity basically states that your reaction is going to proceed across or through your most stable carbocation species. So your most stable carbocation species is going to be the more substituted carbocation. That means that our 3' is going to be preferred over our 2', which is going to be preferred over our primary carbocation. And that is because when you have this carbocation, you have this empty p orbital. And that empty p orbital can be stabilized by neighboring alkyl groups, neighboring CC or CH bonds, which can kind of share their electron density with the empty p orbital and stabilize it more than something that's less substituted. So we're not going to go through our 2' options or our 1' option. We are going to proceed the reaction through our most stable carbocation intermediate, which is our 3' species. Again, because this is the most hyperconjugated system. So continuing the reaction, we had our bromide anion. It can attack the electron-deficient region on that carbocation, producing our final species, which is replicated up here. So that was a little about regioselectivity and carbocation stability when you have multiple double bonds. Thank you.